So the next unit we're going to cover in our course is chemical systems and equilibrium. In your textbook, it shows up as Unit 4 if you're looking for it, and I've put the PDF up online for the textbook with the answer key so you can check your work along the way. Now, if we were doing this in class, I would usually start off the lesson with an activity called a coin exchange game. Now, I did post the activity in the lesson folder, and if you have someone else at home, or if you even wanted to simulate it on your own, you could definitely do it. If you don't have coins, you could easily use something like dry pasta noodles, or beans, or little playing chips, but you want roughly 80 to 100 of them for the activity to work. So what I would suggest is, if you can, try that activity out. It'll give you an idea of what equilibrium's all about, just with a physical context, and hopefully that'll help understand some of the lessons that follow. Alright, so first thing we have to do in this unit is introduce what equilibrium is. So there's a few different ways you can describe equilibrium. So let's take a look at what they are, and then we'll look at an example that you might be familiar with. So what is equilibrium? A simple way of thinking about it is, it's a state of dynamic balance. Dynamic means motion, so something that's in motion but's also balancing out. Another example, or another way of describing it, is when two processes are kind of undoing each other at the same rate, at the same time. So it might not look like anything's changing visually to your eye, but there is something happening throughout the process. This example goes really well with the coin exchange activity. So again, if you haven't tried that, if you have some time, which you probably have lots of time right now, maybe try that one out. Finally, one other way of thinking about equilibrium is two opposing processes taking place at equal rates to one another. And this one works really well with tug of war. So hopefully you're familiar with tug of war. Maybe you played it on a team, but this picture here shows just two people involved, one on each team and one on the other. And often in tug of war, there's some kind of flag or marker on the rope that shows where the midpoint is. So if we assume that these two guys are pulling with equal but opposite rates on that rope, so this guy's pulling with a force to the right, and the guy on the left is pulling with a force to the left, but they're equal and opposite to one another, the rope isn't going to move, and neither are they. We know there has to be some force acting on the rope, because here you can see the rope is pulled tight. So we know there's some force or tension within the rope. That wouldn't happen without the two opposite forces taking place at the same time. But when you look at it, nothing appears to be changing. They're pulling, there's a force there, but nothing's changing. And that's kind of what the idea of equilibrium is all about. But what we're going to do now is actually think about it on a molecular level and what happens in chemical reactions. And this is a change from a lot of the typical chemical reactions that we've seen up to this point. So, what are our chemical reactions going to look like now? They're still going to have reactants and products, but you'll probably notice right away there's something that's very different. It's this arrow in here. This is called an equilibrium arrow. And how you draw it, it's basically two half arrows. So imagine drawing one arrow in the forward direction, but only putting half of the arrow in. And then you draw an arrow going in the opposite direction, and then you put that half arrow in. So you've got a force pulling in one direction, and at the same time a force pulling in the other. Or for a chemical reaction, your reactants make the products, and as some of the products form, they revert back and make some of the reactants. So these are reversible reactions now with that equilibrium arrow in it. So when does this take place? There are some conditions that need to be established. So if a reaction is going to be at equilibrium, your forward rate and reverse rate have to equal to one another. So going towards your products in the forward direction or going towards your reactants in the reverse direction. Next, you have to make sure that all of those properties of the equilibrium system don't change. So if you remember from our last unit on energy and rates of reaction, there were some factors that affected the rate of a reaction. Here we want to make sure these things don't change, because then that changes the rate, and then that causes a problem with our first condition there. So things like temperature has to be constant. pH has to be constant. Quantity, that means amounts, have to be constant. We're dealing with concentrations, that has to be constant. And there's more, but all of those things can't change. They have to be constant. Another one, you have to have an isolated system. So remember that term from our previous unit. That means no change in matter, and there's no change in energy or pressure. All of those things. It's in a perfectly isolated system with no changes. And finally, what happens if you did change one of those properties that we talked about above, temperature, pH, quantity, etc.? If the system's at equilibrium, it reacts spontaneously, so right away, and it tries to reestablish that state of equilibrium if there's some kind of stress. We'll talk more about stresses tomorrow, or in our next lesson on Le Chatelier's principle, but that's coming up a little bit later. So stress means change in conditions. That's the easiest way to think about it. So now what we're going to do is introduce a constant that we use quite a bit in equilibrium. It's similar to the constant K that we saw in rate laws before, but it's a little bit different. And this forms the basis for how we're going to solve a lot of our equilibrium problems going forward. So let's take a look at this K value. So our equilibrium constant expression is called KEQ. It's a capital K and it has subscripted E and a Q for equilibrium. Sometimes that's there, or sometimes it's just a capital K on its own. That will vary from source to source. So what does this have to do with rates and rate laws, and how do we come up with the expression? So we're going to look at an example to help us with this. So here's our example. Nitrogen and hydrogen combining to make ammonia, and here we see that equilibrium arrow. So we know it's a reversible reaction. And one of the conditions we said for reversible reaction, one at equilibrium, your forward rate of reaction has to equal the reverse rate of the reaction. And we know we can write out rate laws for both of those directions, forward and reverse. So if you remember back to rate law from our last unit, we've got our rate law constant. We're putting the direction in here just for reference, forward. Our two reactants in here. And this is an example of an elementary step. So the exponents, the coefficients, become the exponents in this rate law. The reverse direction is going backwards, where ammonia is our only reactant. So ammonia is in here, and the 2 there comes again from the coefficient. So essentially what we have now is an equilibrium expression, but it's a little bit busy and maybe not in the best format for what we're going to use. So we're going to show you where KEQ comes from because I think that that's helpful, but it involves a little bit of rearranging. We won't have to do this with every example afterwards, but I think it helps for people to know where it actually comes from. So what we're going to do, we're going to put all of our K values on this side. So since we already have the forward here, we're going to leave it exactly where it is. We want to move this K value to the other side, and we know it's going from numerator. When we move it to the other side of the equal sign, it goes in the denominator. So now we've got K, our our rate law constant on the top, and now we have our rate law constant on the bottom for reverse. On the other side of the equal sign, we're going to put everything in concentration. So since the ammonia is already there, we're going to leave it. And now we have to move our nitrogen and hydrogen from the numerator, and they're going to come down and go in the denominator. Everything else with it stays the same, all of the exponents. And now what we do is we're going to replace these two rate law constants with KEQ. So the equilibrium constant KEQ is a combination of the forward and reverse rate law constant values. Everything over here does not change. And that would be the equilibrium expression for the particular reaction above, nitrogen and hydrogen producing ammonia. So, in general, now that we know how this is derived from a specific reaction, we can come up with a general expression for equilibrium. So, in general, anytime you have an equilibrium constant, it's going to be a combination of your products, which sit on the top. Remember, ammonia was product. So your product concentration on the top, and on the bottom, you're going to have all of your reactant concentration. We always look at it in the forward direction. So these are our forward direction reactants, and this is our our forward direction product. Also to note in here, just a reminder, square brackets is going to mean concentration in moles per liter. So make sure that you're using moles per liter for this equation. So now let's add a little bit more to our generic expression. So this is saying we need our products over our reactants for a reversible reaction. So if we took this general reaction here, A, B, C, and D, A and B are reactants, C and D are products, we would get KEQ, and our products go in the numerator. So we would have product C to the exponent C, product D to the exponent D, those are our coefficients. And on the bottom, you're going to put your reactants A, and then you're going to put your other reactant B there. So that's a general rate law expression for an equilibrium reaction, but we don't call it rate law anymore. We're calling it an equilibrium expression, or KEQ value. So let's make sure you can try out one of these on your own. So I'm going to give you a moment to try an example. So given this reaction at equilibrium, could you write out an equilibrium expression for it? So that means, can you write a KEQ expression? So at this point, pause the video, take a minute, and see if you can write out a KEQ expression. All right, so hopefully you've tried this one out. Let's take it up together. So KEQ, products go in the numerator. This is our product. Oops, that's definitely not our product there. That looks better. And the exponent's only 1 because there's a coefficient of 1. So if you want to write in 1, go ahead, or just leave it the way that it is. Then our reactants go on the bottom. So carbon monoxide, exponent of 1, times hydrogen, and it's 2, exponent of 2. So for now, with your practice problems, you'll just practice writing out some K expressions, but in a couple of lessons, we're going to start using this to help us solve for concentrations of all the different components in an equilibrium reaction. To finish off the lesson today, what we're going to do is take a look at K a little bit more. So K, or our KEQ, or different kinds of Ks. So knowing the size or magnitude of the K value actually tells us a lot about the system at equilibrium, and you can get an idea of what the concentrations will be at equilibrium for your reactants and for your products. So these are the 3 scenarios, and I'm going to just scroll this down and put on a diagram that comes from your textbook to try and help us imagine what's going on. So over here in the first diagram, we've got KEQ is greater than 1. If you look at the picture, you can see your products, there's more of them compared to reactants. More red dots than green dots. So up here, your product concentration, there's more of it compared to reactants at equilibrium. We say this means the equilibrium lies far to the right. Remember, KEQ is a combination of your products over your reactants. That's just a ratio. That's all that it is. So if you have more products compared to reactants, and we can actually use these numbers here, there are 8 red dots compared to 4 red dots. 8 divided by 4 is 2. That's greater than 1. That's why our K value here is greater than 1, and it prefers product formation. You're going to have a bigger number of product molecules compared to reactants to get that K greater. Bigger number over a smaller one. The next example, what if K is equal to 1? That means the concentrations of your reactants and products are about equal at equilibrium. So here if we look, we have 6 products over 6 reactants. That will give you a value of 1 for K. So if you ended up with a K equal to 1 or saw that the K was 1, all the concentration ratios are about the same. Then the last scenario, and just make sure you change this here on your notes because I caught that right before we started. What if your K value is very small? So less than 1. It's always going to be a positive number, but it can be really small. That's the opposite to our first scenario. More reactants compared to products at equilibrium. So down here in our diagram, if you have a look, there are more reactants than products. More green dots compared to red dots. So if we actually did the same comparison, this is 4 dots, our product, over 8 dots, our reactant. Now we're getting a value of 0.5. 0.5 is less than 1. So that tells us that in this equilibrium, it prefers the reactants. There's always going to be more reactants compared to products if your K value is less than 1. So hopefully that helped introduce equilibrium a little bit more. I strongly recommend reading through the textbook as well as part of your review because there's more examples in there that'll help you understand, and trying all the problems that you can. Understanding more about equilibrium at the beginning of this unit will really help you understand the concepts that follow.